And our next speaker is a senior advisor of VTT Technical Research Center of Finland, one of the leading research and technology company in the Nordic countries. He will present the topic Biomass Gasification Process R&D for Power, Heat and Chemicals. Please welcome to the stage Dr. Pekka Simell.
Tere päivästä, lukepeetut kuulijat. Suur tänu Kasparille veel kord kutsu eest tulla pitämään VTT ettepanet siia Tallinnassa. I'm now used all my Estonian skills and I'm better to change to English. And what I'm going to talk about now, we were talking about liquids, we will change to gas phase. And this is on the second pillar of the research and development of work. I have been 40 years as working at VTT in the area of gasification, syngas treated, and Kaspar introduced me to keep this quite general level, so don't go too much on details. But it's a little bit old story, a long story about R&D, and I hope that I can this way share some of the experience we have got during this journey to you, what has gone right and what has gone not so well and on different phases. So at VTT we are working very much on this let's say early phase, and it usually ends here in piloting and introduction to market and demonstration. And so concept validation, laboratory testing, and so here what we are doing very much is working in the valley of death. So in a phase where the cost increase, the economic risk is very big, but you hope to lower the uncertainty level of the work. The time span is very long, can be 20 years. As in this case. And so there is a lot of things. First, I'm talking about gasification-based processes. And just to give you a short idea about gasification, it's a combustion in understoichiometric air. So we put air, steam or oxygen, and the aim is to have a gas that contains carbon monoxide, hydrogen, which can then be used for synthesis or gas combustion in engines or turbines for energy production, but quite recently on chemicals. That's shortly about, let's say, gasification. The problem, this looks nice, but the problem is here, the compounds that make the gas very dirty, so tars, so causing a lot of problems in downstream piping, and so that has been the main goal, to treat the tars, and you can wash them, but there is also other means. And one of the first questions when we started this work in 85 was what are the means, and could we do it by catalytic cleaning of the gas. And challenges are really that the gas contains a lot of impurities. In addition to the main components, we should remove all this and have a catalyst lifetime over 2 years, and work on let's say to have a catalyst that tolerates poisoning and how deals nicely with the process interruptions and so on. And we started this in late 80s by screening the catalyst by after literature survey, what catalysts are good, and making also own judgment. And we started with the real gases. We did a selection not to do in the lab, but to do it in a real environment to get an idea about how it works in practice. As it was a little bit tedious, but later it showed that it was a really good choice. So we had a test unit in a gasification plant, and we traveled there and made the measurements and so on, and found out that there are group of catalysts. Here is the tar content, and like nickel, catalysts work very well in this environment. And we got almost well, the problem seemed to be solved. Fine. The next question is, when this was a lab scale, 50 milliliter reactor, how to do that apply the catalyst in practice. The gas contains dust and all nasty things. And we ended up to use a monolith catalyst. We tested it in a little bit larger scale. I looked at the operational limits and also the fundamentals. What is the chemistry about in this? Is it cracking as it was, or reforming, or what is happening there? I did my doctor thesis on this phase on 90s. This is an example of we already had a quite big. It's a pressure vessel. Actually, the reactor itself is not very big. And what we did is that we measured in serious test runs. This is a time on stream, 500 hours, and about the impurity levels of benzene and tars. That the conversion remained quite high. Looks really good. This works, and everything was quite positive. So the next step was to scale up to a little bit larger. The units in gasification are very big, tens or hundreds of megawatts. And how to do the scaling up? We did a lot of, let's say, reactor testing, this kind of two-phase reactor where the monoliths are here and with the air introduction. So this was already a several meters long unit, but still working in our pilot center at VTT. And also long-term stability testing is one of the key issues. So the catalyst lifetime should be in the range of several years. And we were now on the year 1995, something like that. And to look for the long-term stability test, we had a slipstream unit in Lahti unit. This is just showing you the graph that we had a catalyst reactor that was automatically operating, and we were monitoring it through internet and see how it operates. Over 4,000 hours, operation hours was gained during 2 years of operation. And the end result was that here is time on stream on the longest test run. Conversions were quite high on 2,300. We had a cooperation with BASF, and their practice is that if the catalyst lifetime in this kind of conditions is over 2,000 hours, then you can be quite sure that it will operate also nicely on real life. This is an example of the unit. It was assembled there beside the gasifier, and it operated quite well. Then everything was fine, and we entered to the valley of death of where can we find a customer and site for an industrial-sized demo. And this was a tricky part because it was actually quite difficult to find a demo candidate. That means a person, the CEO or technical manager of the plant that is enthusiastic guy, and also a company that is willing to take the risk and house or invest on this kind of project. So a combination of enthusiasm, risk tolerance, and capacity, and patience is needed from the company. It was really hard to go. The power plant size is 5 megawatts, which is usually they are municipal authorities. So you, in addition to the company, you have to convince also the town council about the sensibility of this kind of investment of several millions of euros. And also the funding and cost increase is really tenfold at least. So from 500,000 euros you will go to 5 to 10 million euros in a plant investment, which means that subsidies are needed from EU, Business Finland, etc. And so building up a demo project to support all the activities, it was also one of the tasks. So it took about, in this case, what I'm talking about, 3 years to get everything on place. There were several candidates, and we did a lot of traveling and talking on that time. And finally, we found out at Kokemäki town in Finland, a place where they agreed after 1 year negotiations to do. And here is a photograph from the contract signing. This is a quiz. Try to guess who is the salesman and who is the customer. And this is Ilkka Haavisto of the Condense, the CEO, and here's the plant manager Jukka Järvenpää. Both nice guys, really working. And this was the idea of the plant. So 3 engines making power, and with the gasifier, tar reformer, and filters and scrubbers and so on. Cost about 5 million euros and production efficiency of 30%. That was in 2005 when we started to construct the unit. So here is the site. The reformer is actually this green one, what is going installed in the unit, and there was also reactor technology development taking place on the same time on the site. And on the same time as in this Kokemäki plant, in Skive in Denmark there was quite a similar plant with a different, let's say, background. Another company from Finland that was selling, it was also our technology, and it was built in 2005. There was a much bigger muscles behind. There was the Department of Energy of the United States, and then Danish Ministry of Energy, and also EU and municipalities. It was a much better organized project, and the Skive plant is working today, but the Kokemäki failed in a few years. Okay, here is the, let's say, the technology that was constructed. So 3-phase catalytic reactor. That there are actually several reactors packed in one reactor, and that was the end result of the work. And this was utilized later, as you can soon see. The story continues. The Kokemäki case failed because it was a really short period of time that was possible to operate there, and also the project was dimensioned wrongly, so it was too ambitious, and it was tuned to really ambitious schedule, and it didn't work on that way. So after a couple of years of testing, we were almost at the end, but it was failing because we couldn't get it operating on the frame of budget. The Skive plant had a lot of monetary resources, and it went much nicer way. And so, however, the story continues. As a second phase, there was the biomass, the liquid demo plant. So the same technology that was used here can be used to make biodiesel. There was 2008, 2011 Neste Stora Enso joint operation project that the aim was to produce in a very large plant, 300 megawatts biodiesel from wood. In connection to a pulp mill, so that was a really big target there. And the second, what is quite recently, I'm working very much right now on here, on its power to X applications. So the same technology can be used for carbon dioxide utilization for fuels and chemicals. But on that time, the target was really on very big plants, ocean blown, but why there aren't still after 10, 15 years of development, no such plans. And in this kind of, there are very high economical challenges of a first-of-a-kind plant. So investment is typically 50% higher. 100,000 tons per year plant will require 500 to 1,000 million euro investment. And so there is a very big risk on. Also risk in showing this kind of slides, and political uncertainties are one of the issues which is related also to all biomass and bio-based processes, and so that has been one of the issues we have been struggling with, and so what we concluded that there is we have to smaller the plant size. Improve the economics by simplifying it and trying. And one of the ideas was that we have a 100 megawatt to 50 megawatt plant sizes and use a numerous of these plants that feed a central refinery with the feedstock, and then we can make a jet fuel or maritime fuel. And like in Komsun project, we had a target of 0.8 euros per liter of diesel price, and all the piloting test was done. You can see on the project site it was ended some years ago, and so technically the concept seems ready. Techno-economic evaluation is one of very important tools that we use in every project. So even in early phase, so analyzing what is the economics of the plant. That this is just an example of what we do. So here is the price of the fuel and different concepts, and the HVO target or price is here, and so we should go on the same level with these costs, and that kind of it's based very often to Aspen models, but in simple case it Excel sheets, but really important tool, and my colleagues have been publishing a lot of these, and if you're interested, there are a lot of publications on techno-economics on gasification-based plants. And so, lessons learned. The initial phase, early phase, so when you are starting the project, it was a good choice to make the test in a real environment, because then we found out that what was the real problem. It was the sulfur that is the biggest or trickiest poison, and then also dust, and we realized that kind of problems, which led us to conclude that we need a kind of monolith type of structure in the industrial scale. And in pilot scale, techno-economic life cycle analysis is very important, and reactor concept studies, also reactor modeling, flow modeling of how you really construct the system, and also to study the long-lasting phenomena like corrosion and poisoning and that sort of ideas. And in full scale, like the Kokemäki failed because ambitious schedule. First time not tested unit were connected together, and when they fail, each after another, it's very tricky to fix first the feeding and then the gasifier and then the reformer, and that it's better to do a phased, even it's longer and more expensive, but just to really cut it in pieces and do it that way. The Danish site was done quite a similar way, but they had a very much higher budget and more time on doing that. And also demo plant calls a lot of R&D work, which this kind of small companies run with a few persons. they usually don't have the support on that. So it's also one issue that really resources and experience is needed. It's not just the enthusiasm, but that helps a lot. But that also that's very important. And small players very often run out of that. So, Aita, thank you for your attention.
So thank you, Pekka. And now we have time for questions. If there is no questions at the moment, then thank you for a nice presentation.
Thanks.